It could not know. That is not a poetic hedge. It is a physical fact. A photon has no internal clock. It carries no memory of its emission. From the photon's reference frame, something even stranger is true. No time passes at all. The moment of creation and the moment of detection are, for the photon itself, the same moment. It is born and it arrives simultaneously in a single instant that spans 13 billion years of cosmic history from our side of the equation. We experience this journey as an almost incomprehensible span of time. The photon experiences it as nothing, not as a fast passage, not as a blur, but as a zero, a duration of exactly zero. The distance is real. The time is real. But the photon is exempt from both. That asymmetry, the 13 billion years we measure versus the zero the photon experiences, is not a paradox to be resolved. It is the structure of the universe, as Einstein described it when he was working as a patent examiner in Bern and, in the evenings, writing physics. Albert Einstein completed his paper on special relativity in June of 1905. He was at a wooden desk in the patent office, other people's technical drawings stacked beside him, and the theory he was writing did not derive from any experimental anomaly. He derived it from a constraint. If the laws of physics are the same for all observers, light cannot travel at different speeds for different observers. That single requirement rewrites the geometry of time. The photon we are following was emitted, not created in any mystical sense, but converted from energy to radiation in one of the most violent processes the universe permits, from a quasar. The word quasar is a compression of quasi-stellar radio source, a label invented in the 1960s, because astronomers did not yet know what these things were. They looked like stars in photographs, but had spectra that made no sense for stars. Martin Schmidt was sitting at the Palomar Observatory in California in 1963, comparing photographic plates against spectral readings when he stopped. The object he was analyzing, a radio source that looked like a faint blue star, had emission lines that did not match any known element at rest. They were shifted so far toward the red end of the spectrum that Schmidt initially assumed contamination, instrument error, something mundane. Then he recognized the pattern. It was hydrogen. Ordinary hydrogen. But the source was moving away from us at a velocity that placed it at a distance no one had thought possible for a star-like object. He put his pencil down and told his colleagues, "This thing is not a star, and it is not nearby." What Schmidt had found, and what we now understand, is a quasar, a galactic nucleus in which a supermassive black hole is actively consuming surrounding matter. Not passively consuming, which would be quiet. Actively, the infalling material forms a disk, and the friction in that disk generates heat and radiation at a rate that can outshine an entire galaxy of 400 billion stars. Our photon came from one of these engines. The specific quasar that emitted our photon existed when the universe was less than 1 billion years old. At that point, the universe was denser, hotter, and structured differently than it is today. Galaxy clusters had not yet settled into their current configurations. The filaments and voids of the cosmic web were still assembling. Into this environment, a black hole with a mass several billion times that of our Sun was already operating, already feeding, already broadcasting across frequencies that nothing alive yet existed to receive. The photon left this engine at the speed of light. Every photon leaves at exactly the speed of light, not approximately, not as a default, but as a constraint built into the fabric of spacetime. Light has no mass, and massless particles cannot travel at any other speed. This is not a rule that light obeys. It is what light is. Here is what the photon did not experience. It did not experience the first 3 billion years of its journey, during which the universe expanded by a factor that stretched the very space the photon was crossing. This is not a trivial detail. When we say the photon traveled 13 billion light-years, we are measuring the current distance to the quasar, accounting for cosmic expansion. The photon did not travel through a static medium. The medium was moving. Space itself was stretching, and the photon was carried along with it, its wavelength stretched in the process, its frequency dropping, its energy decreasing. This is what we observe as redshift. The photon that arrives at our detector is not the same photon that left the quasar, not in its properties. It has been redshifted, diluted by expansion, converted from high-energy ultraviolet to something we can detect in the infrared. But it is the same quantum event, the same entity, carrying the same record of its origin. It did not experience the formation of the first stars. Roughly 200 million years after the Big Bang, while our photon was still in transit, the first generation of stars ignited in the universe. They were enormous by modern standards, perhaps hundreds of times the mass of our sun, burning hot and fast, fusing hydrogen into helium and then into heavier elements, dying in supernovae that seeded the surrounding gas with carbon, oxygen, iron, the building blocks that would eventually make planets, and on at least one of them, something capable of asking questions. The photon did not notice any of this. It traveled through the diffuse intergalactic medium, a near vacuum threaded with stray hydrogen atoms in magnetic fields so weak they barely register by any unit we use daily, and it did not accumulate experience. A photon cannot. The concept does not apply. I cannot locate where this asymmetry sits in my understanding of what science is for. The categories I reach for, eerie, clarifying, structural, all fail. Eerie requires something wronged by the situation, and the photon is not wronged. Clarifying suggests the kind of clarity you can use. This is neither. The photon's ignorance of its own journey is not a deficiency. It is what allows us to read the journey at all. If a photon could accumulate information in transit, it would arrive corrupted. The fact that it cannot is the feature, not the flaw. At roughly 500 million years into its journey, our photon passed through what cosmologists call the epoch of reionization. This was the period when the first stars and quasars, objects like the one that emitted our photon, began pouring ultraviolet radiation into the surrounding gas, stripping electrons from hydrogen atoms and converting a foggy neutral universe into the transparent plasma through which light can now travel freely. Before this epoch, the universe was, in the technical sense, opaque to light. Our photon was born just before this boundary and traveled through the transition. The photon crossed the era of peak star formation, roughly 3 billion years into the universe's history, when galaxies were colliding and merging at rates far higher than today, when the rate of new stars forming each year across the universe was perhaps 10 times what it is now. The photon flew through fields of radiation from millions of star-bursting galaxies, none of them interested in it, none of them relevant to its trajectory. It passed near structures that would eventually collapse into galaxy clusters, the largest gravitationally bound objects in the universe, containing thousands of galaxies each. But the photon deflected around their gravitational lenses, its path bent fractionally, still arriving. Gravity bends light. This was confirmed by Arthur Eddington in 1919 during a solar eclipse, when he photographed stars near the edge of the sun and compared their positions against plates taken 6 months earlier when the sun was elsewhere. The stars had shifted, not because they moved, but because the sun's gravity bent the light traveling past it. Eddington stood in a clearing on the island of Principe, off the west coast of Africa, in the middle of a monsoon that nearly prevented any observation at all, and when the clouds parted for the few minutes of totality, his team captured the images. The measurements matched Einstein's prediction, not Newton's. Our photon's path has been bent by every massive object it passed near for 13 billion years. It did not notice. The intergalactic medium has a density of roughly 1 atom per cubic meter. To put that in terms that register, the best vacuum we can produce in a laboratory contains far more particles than this. Stand in a room that has been emptied of all furniture, all air, all people. You are still in a denser environment than the space our photon was crossing. The medium is not empty in any sense that has a terrestrial name. It is something else, a sustained absence that has no analogy except itself. Our photon crossed this medium for most of its journey. For the majority of 13 billion years, there was nothing near it. No stars, no dust, no radiation sources of comparable intensity. The photon traveled through absolute structural vacancy, not even the weak interactions that particles experience when passing through matter, because there was no matter. Then, roughly 5 billion years ago, something changed in the region of space our photon was heading toward. A section of gas and dust, enriched by several generations of stellar nucleosynthesis, the process by which stars fuse lighter elements into heavier ones and then scatter them through their deaths, began to contract under its own gravity. This contraction was not uniform. It was lumpy, turbulent, subject to local density variations that created centers of collapse. One of those centers would become our Sun. The gravitational collapse that formed the solar system took place over roughly 50 million years. At the end of that process, a medium-sized star was burning at its core, and a disk of remaining material was assembling into planets. One settled into the range of distances at which liquid water can exist on a surface. It was the third planet from the new star. Our photon was roughly halfway through its journey when the Earth formed. The Earth did not exist for the first half of this photon's transit. Everything we consider ancient, the Cambrian explosion, the dinosaurs, the first mammals, all of human history, occurred in the second half. The photon was already 6 billion years into its crossing when the first multicellular life appeared on Earth. It was 12 billion years in when our genus appeared in Africa, walking upright, using tools. "5 billion years ago, our photon entered what would eventually become the local group of galaxies. The local group is the cluster of gravitationally bound galaxies that includes our own, a collection of roughly 80 galaxies of varying sizes, dominated by two large spirals, our galaxy and the Andromeda Galaxy, which is currently on a collision course with us at roughly 110 kilometers per second. This collision will occur in approximately 4.5 billion years, and it will not destroy either galaxy so much as merge them, a slow interpenetration lasting hundreds of millions of years, after which a single elliptical galaxy will exist where two spirals once did. Our photon arrived at the local group before this process began, when both spirals were still structurally intact. The Milky Way, from outside, would look like a barred spiral galaxy, a central bar of stars surrounded by spiral arms trailing outward, all embedded in a disk roughly 100,000 light-years in diameter and about 1,000 light-years thick. Our Sun sits in one of the spiral arms, about 26,000 light-years from the galactic center, which means our photon, upon entering the Milky Way, still had 26,000 years of travel remaining. 26,000 years ago, the last Neanderthals were dying out in Europe. Modern humans had been anatomically modern for at least 70,000 years, but had not yet developed agriculture, metallurgy, or writing. The photon entered the galaxy's disk, while humans were drawing animals on cave walls in what is now France. The photon threaded through the disk without interacting with anything. The distances between stars within a galaxy are vast enough that a straight-line path from the galaxy's edge to any specific point within it has a tiny probability of intersecting a star, a planet, or any substantial matter. Our photon traveled through the galaxy the way that most things travel through most spaces, without touching anything, because most of any space is emptiness. In 1993, a group of astronomers at the Space Telescope Science Institute in Baltimore finished submitting a proposal to use a newly operational space telescope for a project that most of their colleagues considered a waste of time. The project was simple: point the telescope at a single patch of empty sky, an area chosen specifically because it contained no bright stars, no known nebulae, no objects of particular interest, and keep it pointed there for 10 consecutive days. The logic was that in the absence of foreground objects, the telescope's sensitivity would allow it to detect galaxies so distant and faint that no existing instrument had seen them. The telescope would be effectively staring into nothing on the bet that nothing was full of something. Robert Williams was the director of the institute at the time. He had discretionary time with the telescope, a block of hours allocated for the director to use as he saw fit. He spent it on this project over the objections of astronomers who argued the time was being wasted. Williams was sitting in his Baltimore office in December of 1995 when the first processed images came back. The patch of empty sky contained more than 3,000 galaxies, some of them among the most distant objects ever observed. The project was named the Hubble Deep Field. It changed what we understood about the number of galaxies in the observable universe, pushing the estimate from tens of billions to hundreds of billions. Our photon was not in that image, but photons from the same era, from the same population of quasars, were. Those images are records of exactly the kind of engine that launched our photon. They are light that left the same neighborhood, the same epoch, traveling the same distance. When you look at the Hubble Deep Field, you are looking at the source population of the photon we are following. The universe does not record its own history. We built telescopes. We pointed them at blank sky. We refused to accept that the universe's history was inaccessible, and then we found it recorded in the most tenuous possible medium, single photons arriving after journeys of billions of years, carrying the spectrum of their origin. Every quasar detection, every galaxy redshift measurement, every cosmological model we have built for the last 60 years, all of it rests on photons that made journeys like the one we are tracking. A photon is not simply a packet of energy with a direction. It carries information. Specifically, it carries frequency, the rate at which its electromagnetic field oscillates. That frequency encodes the conditions of the atom that emitted it. When an electron in a hydrogen atom drops from one energy level to a lower one, it releases a photon at a specific frequency determined by the energy difference between those levels. Every hydrogen atom in the universe, in the same electron transition, releases a photon of exactly the same frequency. Not approximately, exactly. This is why spectroscopy works. The emission lines are a fingerprint, and the fingerprint does not change. Vera Rubin was at the Kitt Peak National Observatory in Arizona in 1970, measuring the rotation curve of the Andromeda Galaxy with a spectrograph she had helped design. The data coming off the detector showed that stars at the galaxy's outer edge were moving at nearly the same velocity as stars close to the center. They should have been moving slower, the same way the outer planets of the solar system orbit more slowly than the inner ones. They were not. She checked the calibration. She checked it again. The measurements she accumulated over the following years showed that the outer regions of galaxies were rotating too fast. The stars at the edges were moving at velocities that the visible mass of the galaxy could not account for. Either the laws of gravity were wrong, or there was mass that could not be seen. There is still mass we cannot see. Whatever is responsible for those rotation curves, the substance we call dark matter, has not been directly detected. Rubin's rotational measurements remain the most direct observational evidence for its existence. She spent the last decades of her life refining that evidence and watching the theoretical community fail to identify what the invisible mass actually was. She died in 2016 without an answer. Our photon is not dark matter. It is visible, by definition, because it is light. But it passed through regions dominated by dark matter for its entire journey. The large-scale structure of the universe, the filaments and voids, the galaxy clusters, and the walls between them is scaffolded by dark matter. The visible galaxies form where the dark matter halos intersect. Our photon's path threaded through a cosmic web whose structural backbone remains unidentified. "13 billion years into its journey, our photon entered the inner solar system. At this point, its wavelength had been stretched by the expansion of the universe to a length far longer than it had at emission. It was no longer the high-energy ultraviolet that a quasar produces at its core. It was now infrared, or near-infrared. The expansion of the universe had done to the photon what stretching a painted rubber band does to the pattern on it, elongated it, preserving the shape but changing the scale. The solar system the photon entered was not the simple gravitational diagram most people carry in their heads. It was structured, turbulent in ways invisible from Earth, full of small bodies on long elliptical orbits, comets from the outer solar reservoir, asteroids in the belt between the fourth and fifth planets, trans-Neptunian objects in the disk beyond the eighth planet. The photon passed through none of these. A straight-line path from outside the system to a detector on Earth's surface passes through almost nothing. 8 minutes from Earth, just the time it takes light to cross the distance from our Sun to our planet, our photon passed through the corona of the Sun. The corona is the outer atmosphere of the Sun, a region of plasma extending millions of kilometers from the solar surface and heated, through mechanisms still debated, to temperatures of about 1,000,000 degrees Celsius, far hotter than the surface below it. Eugene Parker was sitting at the University of Chicago in 1958 when he proposed that the corona was not static, but was constantly streaming outward as a plasma wind. His paper was rejected by reviewers who called the physics impossible. It was published because the editor overruled the referees. 4 years later, the Mariner mission confirmed the solar wind's existence. The mechanism heating the corona remains unexplained. Our photon passed through this unexplained region in a fraction of a second and continued toward Earth. It crossed the Moon's orbit without deflection. It entered Earth's atmosphere, where most photons scatter and change direction before reaching the ground. Our photon, by the same statistical logic that carried it through 13 billion light-years without striking anything, made it through. A telescope mirror is a curved surface designed to collect and focus incoming light. The largest optical telescopes currently in operation have primary mirrors between 8 and 10 meters in diameter. The photon we are tracking arrived at one of these mirrors, a surface of carefully shaped glass coated with a thin layer of aluminum, polished to tolerances measured in nanometers, housed in a structure weighing hundreds of tons and capable of tracking the apparent motion of a star across the sky with an accuracy of a fraction of an arc-second. The mirror was pointed by a team of astronomers running a survey of distant quasars. A survey sweeps a region of sky, collects all photons arriving from that direction during the exposure, and records them. Our photon arrived during an exposure. It struck the mirror. It was reflected to a secondary mirror, then directed to a detector, an array of silicon-based sensors that converts photon strikes into electrical signals. The sensor recorded the impact. The electrical signal was digitized, stored, and eventually processed. At the moment of impact, the photon ceased to exist as a photon. In quantum mechanics, the process of detection is the process of absorption. The photon's energy is transferred to an electron in the detector material, promoting it to a higher energy level, generating the electrical signal we record. The photon is absorbed. It is gone. Its 13 billion years of transit ended in an interaction with a silicon atom in a camera chip. The record it left behind, a pixel value in a data file on an astronomer's server, is all that remains. That data file was analyzed. The photon's frequency, shifted by the universe's expansion, was measured against known spectral lines. Working backward from the redshift, the degree to which the frequency had been stretched, the distance to the source was calculated. The quasar from which it came was identified as one of the most distant objects in the observable universe, existing when the universe was less than 1 billion years old. The photon's properties encoded the conditions of its origin: the temperature of the quasar's disk, the composition of the gas it was emitted from, the velocity at which the source was receding. A single photon, read correctly, is a message from the early universe. The photon carried its frequency intact. It carried the signature of hydrogen, the record of its redshift, the information about its source's luminosity. It could not carry what happened around it. The dark matter it passed through left no imprint on the photon. Dark matter does not interact with light through the electromagnetic force. It interacts gravitationally, bending the photon's path in ways that are detectable only statistically, by comparing the positions of thousands of background objects and measuring the systematic distortions in their apparent positions. This technique, called gravitational lensing, was calculated first by Fritz Zwicky. Zwicky was sitting in his office at the California Institute of Technology in Pasadena in 1937, working through what Einstein's equations implied for clusters of galaxies, when he calculated something the data could not yet confirm. A massive cluster would act as a gravitational lens, bending the light of objects behind it, distorting their apparent positions. Measuring those distortions would reveal the cluster's total mass, including any mass too dark to see. He published the paper. The instruments needed to test it would not exist for another 50 years. Our photon's path was bent by every mass concentration it passed near for 13 billion years. Those bends were tiny individually. But the cumulative lensing record, distributed across thousands of photons from the same survey, encodes the distribution of dark matter along the line of sight. Single photons cannot be read this way. Our photon alone tells us almost nothing about the dark matter it passed through. It is one data point in a statistical argument that requires millions. The photon also could not tell us about its own source's environment, not directly. The region around the quasar's black hole, within the accretion disk, is opaque to optical light. The photon we detected came from the outer disk, where the plasma is cooler and the opacity lower. The innermost regions, where general relativity and quantum mechanics are both required simultaneously and where their predictions are not yet reconciled, are hidden behind a photon sphere of their own making. We built an instrument spanning the entire Earth, synchronized radio dishes on 6 continents, to image the shadow of a black hole. The image published in 2019 showed a ring of light around a central shadow, the boundary where our physics runs out. The quasar that emitted our photon contains an object like that, but larger, older, more violently fed. We cannot image it directly. Our photon came from the region just outside it, the last place from which light can escape. An astronomer looks at the data file and reads the photon's record. She is sitting at a desk. Outside the window of the observatory's control room, it is 4 in the morning. The mountain is cold. The dome has been open since sunset. She's been reducing data for 6 hours, checking calibration files, removing cosmic ray hits from the images, running the spectral extraction pipeline. When the output loads, she looks at the redshift value. She does this every night. She knows what she's looking at. But there is a moment, not long, not dramatic, where the number on the screen requires a brief recalibration of scale. A redshift of 7 places the source at the edge of the observable universe, in a time when the universe was less than 1 billion years old. The photon in the data arrived from that time. It left before the Earth existed, before the Sun existed, before the galaxy had its current structure. She types a note into her observation log and moves on to the next object. She does not think about this the way I am thinking about it now. She cannot afford to. She has 40 more objects before dawn. But the number is there, in the log, next to the timestamp of last night's observation. The photon's journey reduced to a single value, 13 billion years stored as a decimal. The photon did not experience its journey. The universe expanded around it without its awareness. Stars formed and died. Galaxies merged. Life appeared on one planet in one galaxy, and eventually built a machine capable of catching a single quantum of light and extracting from it the conditions of a quasar's disk from before the Earth existed. I am certain of very few things about cosmology that feel personal rather than technical. This is one of them. The fact that we are the only process in the universe that records the universe's own history is not a side note. It is the central fact of what science is, not a method, not an institution, a function, the universe's only mechanism for knowing itself. I hold that with more conviction than I can defend philosophically, and I have stopped trying to defend it. You looked at the night sky at some point. Each point of light is a record of a different moment in the past, near stars from centuries ago, distant galaxies from billions of years ago. You are not looking at space. That is not nostalgia. That is physics.